In this video, I'm going to be covering Chapter 9, Properties of Gases. Now, there are two main focuses of this chapter, the ideal gas law and the kinetic molecular theory. There are also a few other smaller topics that we will have to cover as well, but most of what I will be talking about has to do with both the kinetic molecular theory and the ideal gas law. So let's start by talking about the properties of gases. Now, they can all be seen on this slide here. And the ones that we will run into most in terms of the ideal gas law are these ones here, as well as a little bit of this one. And we will also talk a little bit about the densities of gases. Now, the other properties of gases that are on this slide are also important. So gases are miscible. So that means that you can take any gas and mix it with any amount of any other gas. Miscible just means that you can mix them together and they create a homogeneous solution. They all dissolve in each other. Now, it's hard to think of a gas dissolving in another gas because we're not talking about a solution, but that's sort of how you can think of it. I'll talk a little bit about effusion in the next couple slides. So that just has to do with gases escaping their containers through tiny imperfections. And the last property of gases is that they experience weak, if any, intermolecular forces. So in Chem 121, you talked about intermolecular forces and how they affect condensed phases, so that would be liquids and solids. And you talked about hydrogen bonds and dipole-dipole interactions, dispersion forces, and things like that. But in the gas phase, since the molecules are relatively far apart, they're not going to be experiencing those intermolecular forces. So we're not going to have hydrogen bonds. We're not going to have dipole-dipole interactions. Every molecule of gas is going to act as its own little molecule and not really interact with anything else or any other gas molecule in the area that it occupies. So now let's talk about effusion, diffusion, and the kinetic molecular theory of gases. So as I stated in the last slide, effusion is when gases escape their container through tiny imperfections in that said container. So for example, if you had a balloon and you blew it up with air, over time that balloon would lose volume. So some of that air would seep out of the balloon. Even though that balloon is containing the air, the gases will eventually effuse out of it because of the imperfections in that balloon. Now, if you had another balloon and you filled it up with something like helium, helium is a smaller gas, smaller molecular mass, smaller in molecular weight, so it will effuse more quickly out of that balloon. So if you had two balloons, both the same volume, one filled with air, one filled with helium, the one filled with helium would lose its volume faster because the gas would escape the balloon faster through effusion. So the mathematical equation below here is just there to help you understand the relationship between effusion and the density of the gas and of the molar mass. We're not going to be using the equation, but for some of you it might help you understand the concept. So the rate of effusion is inversely proportional to the density of the gas. So a gas that is more dense is going to effuse more slowly, and it's also inversely proportional to molar mass. So the higher the molar mass, the more slowly that gas will effuse. So now let's talk about the kinetic molecular theory of gases. And what the KMT is, the kinetic molecular theory, is a theory that describes the behavior of gases based on four assumptions. So the assumption number one is that gas molecules have a tiny volume compared to the volume the gas occupies. Assumption two, gas particles do not interact with each other. So again, they have no intermolecular forces that exist between them. The gas molecule collisions are elastic, meaning that there is no lost energy when two molecules collide together or when molecules collide with their container. And the average kinetic energy of the molecule in a gas are proportional to the absolute temperature. So all gas molecules have kinetic energy associated with them. And from physics, you may know that the kinetic energy equals 1/2 mv squared. But we're going to be calling the velocity of the gas u, and we're going to be referring to the root mean square speed of the gases. So if you look at the graph on the right, it shows the fraction of particles on the y-axis and the particle speed on the x-axis. So the area under this curve encompasses all the gas molecules that we are interested in. So they all have different speeds. Some of them are slow, some of them are fast. Most of them have this speed right here, which is associated with UM. The average speed is a little bit higher, as you can see by the dotted line, and the root mean square speed is shown by the solid line, and the root mean square speed is the speed of a particle whose kinetic energy is exactly the same as the average kinetic energy of all particles in a gas. And as you can see in the graph below, we have oxygen, nitrogen, helium, and hydrogen gases. And again, each gas has a distribution of speeds. Some of them are slow, some of them are fast, meaning oxygen has some slow molecules and some faster molecules. Hydrogen has some slow molecules and some fast molecules. But as you can see, oxygen being the largest molecule has the slowest speeds, whereas hydrogen being the smallest molecule has the fastest speeds. So oxygen's root mean square speed is slower than that of nitrogen, which is slower than that of helium, and which is slower than that of hydrogen. So the smaller the molar mass is of a particular gas, the faster it travels. So if we go back to effusion and bring in the kinetic molecular theory of gases and the fact that small molar mass gases travel faster than large molar mass gases, we can start to explain why effusion of helium is faster than the effusion of air out of a balloon. So the gases that have higher speeds are colliding more frequently with the walls of the container, in this case the balloon, so they have more chances to escape. They can escape more quickly than the gases that have lower kinetic energy and are not colliding with the edges of the container as frequently. So we can see this relationship using this mathematical equation, which basically shows us that the effusion rate of one gas is going to be inversely proportional to its molar mass, right? So we have the effusion rate of A is inversely proportional to the molar mass of A, and the effusion rate of B is inversely proportional to the molar mass of B. So again, small molar mass gases are going to effuse faster than large molar mass gases. So diffusion is defined as the spread of one substance through another. And the easiest way to picture this is to picture a glass full of water and then adding a drop of food coloring into that glass and just watching as the food coloring slowly diffuses through the entirety of the water. So initially that drop of food coloring will just occupy a small area of the glass, of the water, but over time, as diffusion happens, the glass will eventually have a uniform color. So a uniform red color, for example. The same thing happens with gases. Now the mean free path is the average distance that a particle can travel through the air or any gas before colliding with another one. So as we've discussed, there are quite large spaces in between each gas molecule. So depending on how dense that gas is or how many molecules there are in a specific space, that's going to determine the mean free path of any particular gas molecule. So if there are lots of gas molecules in a container, the mean free path is going to be small because each gas molecule is going to be more likely to collide with another gas molecule. Whereas if we have a container that is mostly empty, so not very much gas in there, you can think of it as a low pressure gas, then the mean free path of that is going to be a lot larger because the gas molecules are not going to be colliding with each other very often. So now let's quickly talk about atmospheric pressure. So I mentioned pressure in the previous slide. So a low pressure would mean that there are very few gas molecules. A high pressure would be lots of gas molecules in a given area. So what is pressure? It is a force per unit area. And atmospheric pressure, something that we're all exposed to, is measured by something called a barometer. So an easy way to make a barometer would be shown on the right here. So if we have a small capillary and we fill that up with mercury such that when we flip it over, we have a vacuum formed in the top of that capillary. Gravity is going to be pulling that mercury out of the capillary, but at the same time, we're going to have atmospheric pressure pushing down on the surface of the mercury, which will be holding the mercury up in that capillary. So when the atmospheric pressure pushing down on the mercury is equal to the force of gravity pulling the mercury out of the capillary, that's going to give us an idea of what the atmospheric pressure is, and that's going to be based on how high that mercury sits up in that capillary. Now there are lots of different units for pressure. The ones that we will use mostly in this chapter are the standard atmosphere, or ATM. We'll also use millimeters of mercury, torr, and probably a little bit of bar as well. And if you need some conversion factors for pressures, you can use this table here. And in some cases that will become important, as you will see when we start talking about the ideal gas law. So now just a quick thing on atmospheric pressure itself. Why does atmospheric pressure vary with altitude? Well, you can think of the air pressure or the atmospheric pressure being a column of air that is above your specific location. So if you're at sea level, there is a lot of air above you, right? If you just have a column of air above your head, then you can consider that distance, that amount of air is pushing down on you. As you increase your altitude, climbing up a mountain, for example, the amount of air above you is now a lot lower. Okay, there's not as much air up there, so the atmospheric pressure is going to be a lot lower. Okay, so for the next little bit, we're going to be talking about some gas laws, but I want to bring in the ideal gas law right now, just because all the gas laws we're going to be talking about can be seen within the ideal gas law. So here it is, PV equals nRT. P is pressure, V is volume, N is the moles of gas, T is the temperature, and R is the universal gas constant. Now you may notice that I haven't put any units on any of these variables, and I've done that for a reason. And I really want you to get used to looking at the constant in a mathematical equation and using that to help you know which units you need to use in order to get the right answer out of this equation. So you can't just use any units for temperature or pressure or volume. You have to look at the units of the constant in order to determine what units you need to use. So the units for the universal gas constant are liters times atmospheres per mole times Kelvin. So that right there is telling you the units of everything else in this mathematical equation. So temperature has to be in Kelvin, pressure has to be in atmospheres, volume has to be in liters, and moles is just moles. So if you know the units of the constant, and we'll run into this in other mathematical equations in the next chapter and a few other chapters down the road, if you know the units of the constant, you can't really screw up the units in the rest of the equation. Okay, so pay attention to that because that's going to become important a little bit later. Okay, so the first gas law that we're going to talk about is Boyle's law, and it relates pressure to volume. So Boyle's law states that the volume of a gas at constant temperature is inversely proportional to its pressure. Okay, so that is shown right here. Pressure proportional to the inverse volume. And what we can also do is collect the pressure and the volume on the same side of the equation. So pressure times volume equals a constant number. And we can also see that in the ideal gas law. Here's our PV. We know that R is a constant. This law says that our temperature is constant, so that's also constant. And in this case, moles are also constant. So this whole thing, nRT, is our constant. So if nRT is constant, we have constant moles and constant temperature. The pressure of one system, or the ratio of the pressure to the volume of one system, is going to be equal to the ratio of the pressure to the volume of another system, right? So if we have a system at one pressure and it occupies a certain volume, if we know the pressure or the volume of another system, we can figure out what the pressure or the volume is. Now, the way this experiment was done, or the way that this was determined, was by using this hook-shaped glass apparatus. So if we expose that glass container to, for example, atmospheric pressure, so everything around it and inside it is atmospheric pressure, then we add some mercury to it, and what the mercury is doing is it is separating one side of that apparatus from another. Now, if the mercury in this container is such that the level is equal, so the height of mercury on one side of the U is the same as the height of mercury on the other side of the U, we can say that the pressure on both sides is the same. Now, if we keep increasing the amount of mercury, shown in the last diagram here, we notice that we get a difference in the height of that mercury. And that is because we're essentially squishing this side. So we're increasing the pressure in that sealed end, and that is able to push the mercury such that we have a difference in height here. So we still have atmospheric pressure pushing down here, but on the left-hand side, we're going to have a different pressure in there. And that pressure is going to be proportional to the volume. So we can relate this back to the kinetic molecular theory. So the kinetic molecular theory is talking about the speeds of gases and how quickly and how frequently they are striking the surface of their container. So as we increase the pressure, or as the pressure is increased, the gases are colliding more frequently with the surface of the mercury. So the surface of the mercury being right there. So let's just go through a quick practice using Boyle's law. So we have a balloon at a party inflated with 5 liters of helium at sea level, and we have atmospheric pressure as being 1 atmosphere at sea level. If the balloon starts ascending to 1,600 meters, where the pressure is 0.083 atmospheres, what's going to be the volume of the balloon, assuming the temperature doesn't change? Okay, so we can use Boyle's law. We know pressure 1, that's 1 atmosphere, volume 1, 5 liters, and we also have a pressure 2, and that's going to be the 0.83 atmospheres. And we're asked, basically, what's the volume going to be? So we simply have to rearrange that equation. I'm going to solve for volume. Volume equals P1V1 divided by P2. Plug in the numbers and we get 6 liters out of that. Now, as with any math that you do in this class, it's always a good idea to make sure that your answer makes sense. So we got to think about this a little bit. We initially had 5 liters at 1 atmosphere. Now we have a lower pressure. The balloon has ascended to a higher altitude. The pressure around that balloon is lower, so you'd expect the gas inside the balloon to increase in volume because it's experiencing a lower pressure on the outside. So we have a higher volume as our answer, 6 liters, so our answer makes sense. Now Charles' law, another one of the gas laws, relates volume and temperature. And it says that the volume of a gas at a constant pressure is directly proportional to its absolute temperature. So here we go, we got volume being proportional to temperature at a constant pressure and number of moles. And we can rearrange that, so we have volume over temperature equals a constant. Now again, we can look at the ideal gas law and do the same thing. We can rearrange this equation, so we have V over T equals NR over P. Right? And what we're saying in this law is that the pressure is constant, the moles are constant, and we already know that R is constant, so again, this side of the equation is constant. So just like Boyle's law, if we know the volume and the temperature of one system, and say we know the volume of system 2, we can figure out what temperature that system must be at. Or conversely, if we know the temperature of system 2, we should be able to figure out what volume that system would occupy. So if we were to observe this experimentally, what we could do is we could take a container, cool it down, so the gas inside that container is cold, put a balloon on top of it, and then it would kind of look like this diagram where the balloon is kind of floppy. Then we can take that same container, put it into a boiling water bath, for example, and then what would happen is that the system would increase in volume, and that would be mostly observed by the increasing volume of that balloon. Okay, so again, kinetic molecular theory states that if we increase the temperature of a gas, the gas starts moving faster, the frequency of collisions with the container increases, and that's going to increase the volume of a non-rigid container, which is what this is, right? A balloon is not a rigid container. Okay, Avogadro's law relates volume to moles, and it says the volume of a gas at a constant pressure and temperature is directly proportional to the moles of the gas particles within the system. Right? So we have volume being proportional to moles, or again, if you rearrange that, volume over moles equals a constant. And just like we've done before, we can rearrange this to be volume over moles equals RT over pressure. Okay, we're saying that we have a constant pressure in this law here, and we also have a constant temperature. So again, this side of the equation is constant. So this basically says that if you have a container that's, say, connected to a piston. So for example, if we had something like this, a container, and then a movable piston, right, that piston can go up and down, and then inside there we have a certain number of moles of gas, and that piston is sort of stuck where it is right now. Now what if we added some gas to that system, so add gas? What would you expect to happen? If it's a movable piston, you would expect that piston to move up. Okay, and that's what Avogadro's law is saying. Montanza's law relates pressure and temperature. So in a rigid container in this case, so the containers we've been talking about previously were ones that can move, right? We have a piston that can move up and down. We have a balloon that can expand in volume. In this case, we're just talking about something that is a rigid container. It can't move. So in a rigid container, the pressure of a gas is proportional to its absolute temperature. Right? So we have P proportional to T, and again, P over T is constant. From the ideal gas law, P over T equals NR over V. Right? So it's this rigid container, volume is going to be constant. And also in a rigid container, we can't add anything to it, so the moles are going to be constant. So again, this side of the equation is constant. And if we know the pressure and the temperature of one system, all we need to know is the pressure or the temperature of a second system, and we can determine the other variable. So an increase in temperature increases the frequency of collisions, which causes an increase in pressure. Right? So that's the relationship of this law to the kinetic molecular theory. Now Boyle's law and Montan's law can be combined to this here. So PV over T of system 1 equals PV over T for system 2. And as we've been doing for the rest of them, let's relate that to the ideal gas law. So PV over T equals NR. So Montan's law talks about a rigid container, so the moles are going to have to be the same. And R is a constant, so again, everything on the right side of that expression is a constant. So let's do a quick example using the combined gas law. So the pressure inside a weather balloon as it is released is 798 millimeters of mercury. If the volume and temperature are as follows, 131 liters and 20 degrees Celsius, what is the volume of the balloon when it reaches an altitude where the internal pressure is 235 millimeters of mercury and the temperature is minus 52 degrees Celsius? So when using any of these gas laws, not the ideal gas law, that's excluded from what I'm about to say. So any of these individual gas laws, Boyle's law, Charles' law, Montan's law, and Avogadro's law, it doesn't matter what units of pressure you use, it doesn't matter what units of volume you use, but you must still use the temperature in Kelvin. Otherwise, in this example in particular, that minus sign is really going to screw things up. Okay, so what we can do is we can just rearrange this equation. Okay, we're trying to solve for V2. Okay, so we rearrange the equation, solve for V2, convert our Celsius degrees into Kelvin. So remember, 0 degrees Celsius is 273.15 Kelvin. In this case, we just use 273. So 20 degrees Celsius is going to be 293, and minus 52 is going to be 221. And if we run through this calculation, we end up getting 336 liters. So again, does this make sense? We have a weather balloon released at 798 millimeters of mercury. It ascends to an altitude where the pressure is 235 millimeters of mercury. So the pressure is a lot less. We expect the volume to increase, and that's what we see. Right? 336 liters versus 131 liters. So now we finally get to the ideal gas law, and we've already talked about this in the last few slides, and we've also seen some of the assumptions of gases on the very first slide of this particular chapter. So the volumes of the individual gases are insignificant compared to the overall volume, and the particles do not interact with each other. So those assumptions are necessary in order for the ideal gas law to be true. So again, there it is, PV equals nRT. So now let's do a quick example. How many moles of air must be in a racing bicycle tire with a volume of 2.36 liters if it has an internal pressure of 6.8 atmospheres at 17 degrees Celsius? So we're asked to find moles. We're given PV and T. We know R is a constant. Let's just check to make sure our units are right. We know that pressure must be in atmospheres. It's in atmospheres. Temperature must be in Kelvin. We're going to have to convert that. And volume has to be in liters, so we're good there. Because remember, our units for R are liter atmospheres per mole Kelvin. Now, I haven't actually told you what that number is yet. It's actually 0.08206 liter atmosphere per mole Kelvin. So you don't have to remember this number. This will be on an equation sheet that you will be given for exams. Okay, so since we're solving for moles, we're just going to rearrange the ideal gas law to solve for moles. Make sure we convert our temperature to Kelvin and run through the math. We end up getting 0.67 moles. So one other small thing that you will run into a little bit is something called standard conditions. We'll see this in the next couple of chapters as well, but standard conditions are a little bit different there than they are here. So when we're talking about gases, we have a specific set of conditions that we compare everything else to, sort of a a reference set of conditions. And in this case, it's 0 degrees Celsius and commonly 1 atmosphere of pressure, at least in the United States, but other places around the world might use bar instead of atmosphere. And the difference between a bar and an atmosphere isn't that much, so it's not going to make a huge difference if you use one or the other in a calculation. So a molar volume at standard temperature and pressure is the volume of 1 mole of a gas. So if we have 1 mole of a specific gas at a specific pressure, what volume is it going to be occupying? So if you used 1 atmosphere as your pressure, it would take 22.4 liters. And if you use 1 bar, it would take 22.7 liters. Okay, so that's how much volume 1 mole of gas would occupy at 1 atmosphere of pressure. Right. So now let's very quickly just talk about the densities of gases. So the density of any gas at standard temperature and pressure can be calculated by dividing its molar mass by its molar volume. Right. So we talked about molar volume in the previous slide. And if you want to see this derivation, I have it on the worksheet. It actually comes from the ideal gas law. So here's our molar mass. This is our pressure. This is the universal gas constant, and T is temperature. So again, since we have the universal gas constant R, we must make sure pressure is in atmospheres and temperature is in Kelvin. Okay, molar mass is going to be in grams per mole. So quick example, according to the U.S. National Weather Service, the air temperature in Phoenix reached 26 degrees Celsius on January 1st, 2012, when atmospheric pressure was 1,024 millibars. What was the density of the air? So since we're trying to figure out the density, we can use the equation that we saw on the previous slide. And one thing we're going to have to do is to convert millibars into atmospheres, and we're also going to have to convert 26 Celsius into Kelvin. So by using the table that we saw earlier in this chapter, you could also find that in your textbook. We can convert millibars into atmosphere through this conversion here, and we end up getting 1.012 atmospheres. Right, so now we have our pressure. Temperature 26 degrees Celsius, that's going to end up being 299 Kelvin. So there we have temperature. R we know is 0.08206 liter atmospheres per mole Kelvin. And we have an average molar mass of the air, which is 28.8 grams per mole. So now we have everything we need to solve this problem. So by simply plugging in the numbers, we end up getting a density of 1.19 grams per liter. Now make sure your units are right in these calculations too, right? Atmospheres cancel, kelvins cancel, moles cancel, and we're left with grams per liter. And remember, a density is a mass per volume. So there's one other way we can do this question. We can use the normal density equation, so one that you may have learned in physics or in high school, density equals mass over volume, and combine that with the ideal gas law, rearrange it so we're going to solve for volume, right? We need a volume for our density equation here. So if we use the ideal gas law, we're going to find a molar volume, right? Because we have N here. We can put whatever number we want in there, but it's convenient to just say how much volume is 1 mole going to take up. So there's our 1 mole. We have our universal gas constant, the temperature, and the pressure that we calculated previously. And now since we have the molar mass, we use that as our mass, and we get the same number if we calculate it this way. All right, so this particular section is really small in your textbook, gases and chemical reactions, and it basically says that in a chemical reaction involving a gas as either a reactant or product, the quantity of a gas in moles can be determined from the ideal gas law if we know the volume of the gas and the temperature and pressure at which the reaction proceeds. Okay, so if we have this particular reaction here and we know, say, the volume of C3H8, and we also know the temperature and pressure at which this whole reaction occurs at, we would be able to figure out the moles of the rest of the gases. Now, if you want a quick example of this, you can look on page 422 of your textbook, and that is example 9.11. Okay, so basically you end up looking at the stoichiometry of these particular components of the reaction to help you determine how many moles of that particular gas is there. And the last section I'm going to talk about in this chapter is mixtures of gases. So in a mixture of ideal gases, all gases behave independently of one another, meaning that each gas is going to have a specific pressure associated with it itself. So whereas the total pressure, say the total atmospheric pressure is 1 atmosphere, since the atmosphere is made up of mostly oxygen and nitrogen, Nitrogen is going to make up a certain proportion of that pressure, and oxygen is going to make up the rest of that proportion. So if nitrogen is 80% of the atmosphere, oxygen is 20% of the atmosphere, together they make one atmosphere. Nitrogen would then have 0.8 atmospheres associated with it, and oxygen would have 0.2 atmospheres associated with it. Okay, so each gas exerts its own pressure in that mixture, and it depends on the amount of each gas in the mixture. Right, so the total pressure is going to be the partial pressures of all the gases in a system. So pressure 1 might be oxygen, pressure 2 might be nitrogen, pressure 3 might be carbon dioxide, for example. And all those put together is going to equal the total atmospheric pressure. So now we're going to go back to something that you learned when you talked about solution chemistry in Chem 121. So I think that was chapter 11 in your textbook. So we're going to talk about mole fraction again. So when you learned mole fraction, you learned it as chi equals the moles of the solute divided by the total moles of solution. When we're talking about gases, we're going to be talking about the moles of one of the components, so for example oxygen, divided by the moles of everything, so the moles of all the gases, the moles of nitrogen plus oxygen plus carbon dioxide. So that's going to give you a mole fraction of, for example, oxygen if this was the mole fraction of O2 and this was still total down here. And the partial pressure of that gas, so for example oxygen again, in that mixture exerts a pressure that is proportional to that mole fraction. So the larger the mole fraction, the larger the pressure that that particular gas exerts, and that is shown here. So the pressure of, for example, O2 is going to equal the mole fraction of O2 times the total pressure. So if there was 20% oxygen in the atmosphere, it's going to exert 20% of the total pressure of the atmosphere. So let's just go through an example. We have a gas mixture with a total volume of 2 liters, contains different amounts of nitrogen, hydrogen, and methane. What are the partial pressures of each gas at 10 degrees Celsius? So we're asked for the partial pressure, so we know we need this equation here, because this guy here is partial pressure. What do we need for partial pressure? We need mole fraction, and we need total pressure. Now we have neither of those in the question, so we're going to have to figure them all out. So first, let's try to figure out mole fraction of all of the gases. So chi is going to equal the moles of component A divided by the total moles of everything. So if we want to figure out the mole fraction of H2, it's going to be the moles of H2, right, which is 0.4 moles. The total moles is just going to be adding the 0.4 to the 0.2 to the 0.9, ends up being 1.5 moles. So the mole fraction of H2 is 0.267. Do the same thing with nitrogen and CH4. Now you know you've done this correctly if these all add up to be close to 1. They might not be exactly 1 if there's some rounding errors, but as long as it's close to 1, then you know you've done it right. So now that we have the mole fraction, we have to figure out what the total pressure of the system is. And to do that, we can use the ideal gas law. So we're going to rearrange the ideal gas law, solve for pressure. So we have pressure equals nRT over V. Right? We're given a volume here of 2 liters. We're given a temperature of 10 degrees Celsius, but we're going to have to convert that into Kelvin. And we know the total moles, right, because we're given the moles of each of the gases. So if we just plug in all of our values into the ideal gas law, we have 1.5 moles times the universal gas constant times 283 Kelvin, which is 10 degrees Celsius, and divide that by 2 liters, and we end up getting a total pressure of 17.42 atmospheres. So now we have everything we need to solve for the partial pressures of each of the gases. Right? We have the mole fraction, which we solved a couple slides ago. We have the total pressure. So now we can figure out what the partial pressures of each of the gases are by simply multiplying the mole fraction by the total pressure, and we get our answers here. So it's a good idea to check to see if the answers make sense again. Since the mixture is mostly nitrogen, right, we have 0.9 moles of nitrogen. Nitrogen should have the highest partial pressure, and it does. And we have the least amount of methane, so methane should have the lowest partial pressure, and as you can see, it does. So that's all I have for this chapter. If you have any questions, please feel free to contact me either through email, by coming to my office hours, or by setting up another Zoom appointment so that we can talk about any questions that you may have.